Okay, folks, for the problems, I tried to choose two problems that allow you to show your understanding of momentum and energy conservation or not in collisions, and also don't involve solving a system of equations. So in this first one, I did not write it in the question, but the subtext here is two globs of goo are thrown at one another, and they collide and stick together. Because they're goo. Calculate the amount of energy lost during this collision. I give you the masses of the two globs and the initial velocities of each one. And so to calculate the amount of energy lost, I need to know how much energy there is at the beginning and then how much energy is there at the end. So I'm just going to do some momentum calculation. The idea is I can use conservation of momentum to figure out the final velocity of the goo globs after they have stuck together. So the two globs of goo each have their own momentum value, and then once they stick together, they behave as one object with a final velocity. So if I plug in my numbers, 0.75 times positive 5.5 plus 0.65 times negative 5 equals 0.75 plus 0.65 times VF. And so the final velocity of the two globs of goo is positive 0.625 meters per second. One of the easiest ways to see an inelastic collision losing energy is that if you throw two things at one another, they will definitely both slow down because they're being hit by something moving in the opposite direction. Anyway, now we turn to energy, and I'm going to do this separately just so I can fit it in the paper. So I'm going to do initial kinetic energy calculations. I'm just going to skip writing the equation for now. So I'm going to do the kinetic energy of M1, 1/2 0.75 times 5.5 squared, plus the kinetic energy of M2, so 0.65 times negative 5 squared. Anything with a negative velocity will have a positive kinetic energy still, just because of that squared term. The squared term essentially turns velocity into a speed. And so that's 19.5 joules of kinetic energy. Okay. The final kinetic energy is going to be based on the data that I just figured out using momentum. So they are essentially one object. I don't have to calculate this separately because they're essentially one mass. So I add their masses and I multiply that by 0.625 squared. And that is a tiny 0.27 joules. Cool. So the amount of kinetic energy lost is going to be the change in kinetic energy. And so that's going to be 0.27 joules minus 19.5 joules. And so that's negative 19.2 joules. So technically the answer to this question is 19.2 joules of energy was lost because the change in energy is negative. Right. The next one is a 100% elastic collision. So these are, as I said in the last video, kind of a work of fiction unless you're talking about electrons or other elementary particles colliding. Their data is given, same as the other one, and the question is it possible that their final velocities are negative 4v and positive v? And so this question is answerable by using the two conservation laws. So we are going to start with momentum. And instead of setting up momentum and solving for a variable, I would verify this by saying, well, if it's possible that if these velocities are possible, then the total momentum would be the same. So the initial momentum and the final momentum would be the same value. So I'm going to start with the initial momentum. So that's going to be 2m times v over 2. And then the second object, 3m times negative 2v. I'm going to write versus because I'm just going to compare the before and the after. So this is the initial momentum of the system. And now, imagining that these are the final velocities, I'm going to find the momentum of the system after the collision based on that. So 2m times negative 4v plus 3m times positive v. All right, and so now I'm going to go through and just simplify things. This first term is mv. This second term is negative 6mv. This third term is negative 8mv. And this fourth term is positive 3mv. mv minus 6mv is negative 5mv. And then negative 8mv plus 3mv is negative 5mv. So possible according to momentum. But we haven't done energy yet, and so that's like the final thing. Energy and momentum must be constant in order for this to be possible. So I now turn to energy, and I'm going to calculate the kinetic energy for each object. So the first object, I do 1/2 times 2m times v over 2 quantity squared. For the second object, I do 1/2 times 3m times negative 2v quantity squared. Versus, so that's the before. 1/2 times 2m times negative 4v quantity squared. Plus 1/2 times 3m times v squared. Now, since you're just comparing initial and final energy, and kinetic energy has a 1/2 in it, you could just not write the 1/2, but you know, it's there. Okay, so when I simplify this first term, I have 1/2 times 2 times 1/4. And so that's going to be 1/4 mv squared. This next one is going to be 4 times 3 times 1/2. So that's going to be 6 mv squared. Versus. This next one's going to be 16 times 2 over 2. So that's going to be 16 mv squared. This last one's going to be 3 over 2, so that's 3/2 mv squared. Now I can kind of already see that this is not going to be equal because 16 and 3/2 definitely is not going to equal 6 1/4. And so just to formalize that, 6 1/4 mv squared versus 17.5 mv squared. And this is not possible. So again, in order to be perfectly elastic, both the momentum and the energy have to be constant. But in this case, even though the momentum is constant, the energy is not, and so this is not possible.